GAK, and now we're going to look in more detail at the bonding that's occurring. You've probably got your GAK in a baggie. If not, get to that stage, make sure you've seen what happens between the reactants and the products as you make GAK. And we started off with these materials and asking the question, what bonding is present in each of the reactants and the materials that you're going to use? And really about bonding within the atoms of a molecule and a formula unit if it's ionic. You're really looking at the types of elements that are involved. So for ionic, you're going to be looking at a metal and a non-metal, and for covalent, you're going to be looking at a connection between two non-metallic atoms. So if you look through here, you'll see the ionic borax. The rest here are covalent, and because of the non-metallic elements that are being bonded together. And so the covalent and ionic bonds, they're intramolecular within the molecule or the formula unit of an ionic compound. And here's a summary, and I suggest you just pause this to read what's involved, remind yourself of covalent and ionic bonding. Mm-hmm. So in the GAK experiment, we're going to go to look at the forces between molecules, weaker than the bonds that we're dealing with inside, intra. We're looking at intermolecular forces. And what types of intermolecular forces do you know? Just going to do a summary of them, and we're looking at a dipole-dipole force due to a difference in electronegativity between the two contributing atoms on either side of the bond. And remember, it's a shared pair of electrons, and the element with the highest electronegativity will be pulling the pair of electrons closer to it, and we'll have the delta negative charge. Now, that's when you're looking at differences in electronegativities, but to go down to the hydrogen bond, it's a specific case of a dipole-dipole force between a hydrogen atom and the other atom in the bond being fluorine, oxygen, or nitrogen, and the bond between another molecule that has that as well. And we can also look at London dispersion forces in nonpolar compounds where you have the no separation of charge, except the shared pair of electrons actually is moving. So you'll have a temporary dipole, and that's what the London dispersion forces is all about, a temporary dipole. And you can look at the properties there as well. And so with the GAK, what are these intermolecular, interparticle forces that you've got? And so in borax, it's ionic, electrostatic attraction in a large lattice between positive cations and negative anions. In water, covalent, but it's polar covalent with different electronegativities, oxygen being the delta negative with the higher electronegativity, but it's our special case, hydrogen with oxygen, so this is hydrogen bonding and not just dipole-dipole. And we look at the Pva glue with carbon, hydrogen, oxygen, and again you've got an OH, so you've got oxygen, hydrogen in different molecules, so you're going to have hydrogen bonding there. In did polythene for the plastic baggie, it's non-polar between carbon and hydrogen. Their electronegatives are pretty similar, and so it's really going to be London dispersion forces, or incredibly weak dipole-dipole because there is a slight difference in electronegativity. And then we're going on to look actually at the chemicals involved in the bonding. So borax has the formula Na2B4O7, but in solution it is made up of the borate ion B4OH and then a single negative over the whole ion. And that's what we're going to look at in terms here. To simplify things, we've got the monomer of polyvinyl alcohol, the single unit, and we're going to represent the monomer as a blob with two little connecting arms there. So if we show the polymer, we've joined an awful lot of them together, and some polymers have 10,000 plus joined together. And for the borate ion, you see the structure there with the OH groups, and we're going to represent it as the rectangle, the blue rectangle. And in more detail, we're going to put the delta negatives of the oxygen as the link between to the PVA polymer. And so how is it going to link? It's not due to the charge on the ion. So what we're going to show here is each glue monomer has 3 polar OH groups, but only 2 of them are going to take part in the hydrogen bonding with the borate, and it's going to be the hydrogens on the PVA of the OH and the oxygen on the borate ion of the OH that are going to link. And so you're going to have cross-linking with a polymer chain above, the borate, and below. I'm just showing this with only a single hydrogen bond between a borate ion and the PVA. So you've got a hydrogen bond here. And that's the cross-linking which gives the GAK, the slime, Silly Putty, its properties, though the actual product, Silly Putty, that you can buy has some silicate materials in it as well. So looking at the part of a chain and the 2 hydrogen bonds above each borate and below each borate, showing a really large number of links between them. And as suggested before, if you've looked, there's a neat activity where you make a string of beads. If you've got them, make sure you tie the end bead on. The longer the string, the better, because these polymers are large. And you just put 2 in a cup and then tip it out and see what happens. Then, with your strings, join them together with a baggy tie, the thin wire with a little bit of paper over it, and tie them together and scrunch that up and put it back into the cup and tip it out. And what happens is that explaining the difference between Elmer's glue and the GAK that you have just made. In the GAK experiments, these are the tests you've already done, or that you need to do if you haven't, and to comment on how these different activities took place. How easy was it to pull it into a thin film? How easy was it to break, etc.? And then try and explain each of the observations in terms of cross-linking. Are you actually breaking that cross-linking, breaking the intermolecular forces between the PVA monomers and the borate ions? And to show your understanding, you need to be able to explain the changes that occurred to the reactants during the reaction. That's not just describing them, it's describing what is actually happening as well. And be able to give a definition of a hydrogen bond and draw something simple cartoon showing a borate ion hydrogen bonded to two chains, one above, one below of your Pva glue. And on the picture, your diagram, circle each of the atoms in the hydrogen bond and indicate the partial charges, whether it's a delta plus or a delta negative. Much smaller than an actual minus on an ion. It's not a whole electron that's being moved. And then we're going to look more closely at the formulas, the chemicals that are involved. And you have a polyatomic ion, so you see the charges on the sodium, you see the charge on the borate ion, and you've actually got covalent bonds within the polyatomic ion, but it's an ionic compound overall. And where will this molecule link, this ion link to the glue molecule? You have to remember there are lone pairs of electrons, that the bond between the oxygen and the hydrogen, the shared pair is closer to the oxygen, so you have a dipole. And the arrow there, the plus end is where the electrons in the shared pair are furthest from, and the arrow is going to be your negative end, and the electrons in the shared pair would be closer to that atom here, the oxygen. And so we can put on the dipole charges, and we can do the same with the PVA, looking at the lone pairs of electrons on the oxygen. And remember, with the PVA monomer, only two of those OH groups are actually going to link to borate, a single borate ion. And here we've put on the dipole arrows as well, the oxygen being the delta negative and the hydrogen being the delta positive. So the top here, you've got two PVA monomers, and they're just flipped because one's going to be above the borate ion, one's going to be below the borate ion, and just show one link here, cross-linking, and then, well, we're just putting three borate ions and three monomers of a PVA polymer chain above and below to see what's happening. So pause that just to eyeball what's happening. And to review electronegativities, so you can look here at hydrogen and oxygen and see their difference in electronegativities, and indeed between carbon and hydrogen. We've been talking about PVA, and I've drawn polyvinyl alcohol. There is the PVA glues are sometimes polyvinyl acetate, so I'm giving you the polyvinyl acetate monomer here as well to look at. But the diagrams above, I've used the OH of the hydroxyl groups as the significant one. And a reminder about GAK, Silly Putty in space. We have the Apollo 8 astronauts, first humans to leave Earth's gravitational pull, travel to the moon in preparation for Apollo 11 and the moon landing. So they only did a flyby. Can't use the word only. Incredible. Took some Silly Putty with them, and one of the sources said just as a relaxation material, but they used it to secure their tools to somewhere fixed, as opposed to floating around in a weightless microgravity. And that was in 1968. And then we look, and this is a bit of a stretch because it really wasn't silly putty, but a putty-like material. We look at Space Shuttle Discovery in 2007, which was taking a Harmony module to join into the International Space Station. Now, it had been named Harmony in a competition by pupils of Brown Academy in Alexandria, Virginia, and they actually, the class travelled down to witness the launch. But the crew took with them methods of repairing space shuttle tiles, and they were going to experiment with it, a little bit like a cork gun with a putty-like material, and different from our GAK, had to be applied in two parts. It cured once it was mixed, and you can see the tile repair that was done, but they simulated it in the cargo bay. And final example, some students were able to suggest an experiment to take to the International Space Station. And in 2012, comparing Silly Putty made on the space station with the properties of the same product made the same day on Earth. And they said, what is the effect of microgravity on the formation of Silly Putty, and how do the characteristics of the Silly Putty differ from the Silly Putty made on Earth? And as a final thought here, what experiment would you like to perform in microgravity on the ISS? And so the intermolecular forces that are occurring have a significant effect on the properties of materials.